here, and it's more than you need to know, but some of the vocabulary, anything new, it's hard because different words, different vocabulary, different meanings. What does he mean by evolution? There's like 5 different definitions, I'd say. And by the way, if you're interested in talk to me about that afterwards. You can get a DVD. In fact, look on RTB's website, reasons.org. They have a thing, and it's called Through the Lens, and there are several free videos. Unlike the University of YouTube, free videos, and they're excellent. It'll define, if you look for evolution in the title, it'll define those 5. All right? We're only going to talk about chemical evolution, things happening from, so we say, dirt to going to life. And obviously, if chemical evolution didn't happen by the theory that's proposed naturalistically, that theory, if it didn't happen, that theory is, to make a pun, dead in the water, right? And so tonight I'm going to show a couple of key things. Remember, we're looking at, for keeping it simple, non-life going to life, right? Or some say inorganic, for those have a little bit of chemistry background, to organic or bioorganic. Now, the biggest argument against naturalistic evolution, or any form of it, is, and I'm going to write it down here, is information. Where did this information come? How many have heard of this argument being a very good argument against naturalistic evolution? It's tremendous. And we're going to look at that in a couple weeks, provided I don't get escorted off in a limousine, bulletproof limousine after this talk. All right. But this is important, very important. But for a chemist, there's something we're going to talk about, and that's homochirality. I can't even spell it. Cool word. You could maybe win a bet with it. But this is the key. If you don't have homochirality, I hope you're getting excited, right? Are you excited? If you don't have homochirality built into your molecules, proteins, DNA, RNA, no way. The computer isn't there. It can't survive. So I'm going to talk about the key thing in all this, and that points to a chemist that has unbelievable imagination. So you'll see that. But we're only going to look at proteins tonight. The next time we talk, if allowed, we're going to talk about DNA and RNA, and we'll bring in RNA, proteins, and bring it all together. That'll be the next talk, all right? And I'll try and have the handout of the slides, since I'll be given enough time. I just learned about this invitation last Tuesday. And so I'll give me a chance to work on the slides and give appropriate acknowledgement to the slides I use. Because anytime we give a talk, we should try and have the footnotes there, right? Anytime. That's how anybody does it. Because why do you do that? Because then people can test what you said, right? You know, why are you saying what you're saying? All right. So I'm going to because of the time already, is that fast? Because of the time already, how many of you seen on YouTube this video on transcription? Kind of cool. Well, it's a cartoon, and it's only focusing on that particular aspect of what's going on in a nucleus of a cell, transcription. Come the end of the third part, you will know this like the back of hand. Oh, I know what's going on there. Oh, I know why the homochirality is very important. This is cool. All right. I'm not going to spend time showing it. And here's the next one. Translation. So we have transcription, translation. Does that not sound like language? Right? They already using words to talk about language. And we all know information, data, language comes from what? Comes from a mind. That's the only place it can come from. You cannot generate information by chance. And maybe the third talk, we'll talk about how Richard Dawkins, who's heard of Richard Dawkins? If you haven't, you might be in the dark. Well, we'll talk about how he solved that. He has a program that shows they can be generated by chance. Look, when you see it, you'll laugh. But it's an interesting idea. All right. That was for a pause. So being creative with a title for this this talk, I call it, Is It Soup Yet? Or maybe to be more updated, it should be Got Soup or something like that. And as I already mentioned, we're going to talk about the origin of homochirality and the biomolecules. Remember, I am going to define those clearly. Okay? I'm using the vocabulary. The more I say it, the more it's going to be sinking in. When I was a kid and first saw this homochirality in molecules, I said, wow, that's amazing. Well, why does it have to be that way? You know, you hear a lot of apologists.
What is homochirality?
You're going to get there. I'm going to get there.
Oh, okay.
I'm going to get there. See, you already know how to say it. We're already learning. Good stuff. All right. So we're going to learn why it's so important. All right? And that's important. Always ask the why questions. I found out that some of my atheist buddies are skeptics when they are asking the why and the who. You got somebody there. The Spirit's working on them. Those are the people you need to talk to. All right? So, but the why is the important question. And we're going to look at that and why it is important in life. These are on your notes. These are different organizations that talk about origin of life and all its problems, hurdles. I also have, how many read the Talk Origins? That's an atheist one. Or infidels. You ever check those out? You need to check them out. What are they thinking? That's part of the whole game. Don't just go for your thing that you like. You got to learn the whole scope. And there's a big scope out there. Now, when you open up a textbook, I was going to ask you to bring your biology book, but we never happened. But when you open a textbook, you'll see, if you look at the first line there, this is what happens. We have early Earth. We have an atmosphere filled with some gases, all right? Discharges. Does this sound familiar? There's electric discharge, right? And it creates prebiotic molecules. Things like amino acids, formaldehyde. I was at Paris. Have anybody been to Paris? I'm talking Pisgah Astronomical Research Institute. It's up in the Pisgah forest. That is a former CIA and NASA listening post. I was there when they found formaldehyde so far out in space, it doesn't matter. They went crazy. I'm going, what's going on with this? Well, that's a component to make amino acids. They're on their way to find how life originated. Okay, that sounds good. Nice job. And we need that kind of information. We need that kind of information. All right, so it's forming different types of molecules. And then these gas molecules then get absorbed, dissolution, goes into solution, into water. All right, and now you have this so-called pond somewhere where life begins, right? And that's the next one. You have condensation reactions. That's where different amino acids are supposedly going to be reacting and forming proteins. Guess what? That reaction does not even happen in water. They don't even mention that, and you look in the books. Okay, then as you can read, slowly but surely you get a cell. You have to have a membrane around it, and finally you get to the first thing on the famous tree, the last universal common ancestor. That should all be familiar with you. So we have the molecules formed in space. They're going to solution in the water in some pond somewhere. And eventually we have this self-reproducing cell. Now, everybody's heard of this and seen it many times. It's actually not a good drawing, but who has not heard of the Miller-Urey experiment? Maybe the Stanley Miller experiment, all right? Now you notice there it says what are the gases in? Can you read that? This is also an eye test. It says hydrogen is in there, right? What else is in there? It says methane's in there. It says ammonia is in there. And of course, good old water, which we're going to focus on a little bit because there should be a good talk on water. If you want to come up with a talk, there's so many neat things about water, which I'm sure you already know. So we have these gases. We have this spark, all right? It creates these molecules. It dissociates the atoms in these molecules. They recombine, and then they're swept by the boiling water. The steam pushes it over, it's condensed, and it's collected here. And that's where they found, guess what? Amino acids. But something very important was never mentioned. This is back in 1953. Something was never mentioned. Great experiment. And what does an experiment really prove? It proves when you do this, this is what happens. But what were they were so excited about it, they extrapolated that to, hey, we're on our way. We make the amino acids, we make the proteins, we're on our way. On that previous slide with all those steps, right? They're on their way. Not really. Because it turns out that later, not too long later, it said, hey, sorry, Stanley, it wasn't that atmosphere. It was not hydrogen, methane, ammonia, and water. It wasn't that. It was what? Hydrogen? No. Well, they had some hydrogen. Well, it was carbon dioxide, nitrogen, and water. That's what it was. Guess what happens if you put a discharge into those molecules? Nothing. You don't get amino acids. Not at all. This was the original. This is what the primordial atmosphere was. So it was way off, and everybody acknowledges it, but they still think there's a chance. They still have faith there's a chance. There are many people that have written about this now. Jeffrey Beta, he is a former grad student of Stanley Miller. He's continued this quest because funding is very easy to find a naturalistic method for life forming, all right? And look what he says. But is the prebiotic soup theory a reasonable explanation of the emergence of life? Contemporary geochemists tend to doubt that the primitive atmosphere had the highly reducing composition used by Miller in 1993. So, and you can find this kind of a statement in all of the literature. Now, this is makes a key point too. Finally. Okay. So far, no geochemical evidence for the existence of a prebiotic soup has been published. Indeed, a number of scientists, most scientists, have challenged the prebiotic soup concept, noting that even if it existed, the concentration of the organic building blocks in it would have been too small. This is so key. You have to have a large amount of it. And when they did those experiments, guess what percentage of amino acid in the best experiment that Stanley Miller did? The best amount of amino acids formed was 1 to 2%. Now, what's the rest of the stuff? As a chemist, you're not going to be able to take those amino acids and make proteins with it because of all the other stuff in there. And does anybody see something wrong with this being an atmosphere? An atmosphere, a primordial atmosphere? How many think that hydrogen gas would last in the atmosphere? It wouldn't last. It's lighter than helium. What happens to a helium balloon? I've done a hydrogen balloon. Be careful if you do that. It goes up. Remember, that is a contrived experiment. That shows with those conditions, you'll get amino acids. But there's something critically wrong, and I'm getting to that. Obviously, you know what the critical problem is. It doesn't have homochirality, right? And we're going to talk about that. I could have someone read this. Who wants to read it?
I will.
All right.
An honest man, armed with all the knowledge available to us now, could only state that in some sense the origin of life appears at the moment to almost be a miracle. So many are the conditions which would have to have been satisfied to get it going.
You see who the author is of this book, of this quote? Francis Crick. He's the one that discovered DNA. And in fact, he realized right from the get-go, this thing is impossible to happen naturalistically. Because what did he say? Where did he say it all came from? Panspermia. Some other intelligent beings brought it here. That's still one of the main things that secular scientists say, that that's how it got here. Yes, we believe that something supernatural brought it here, not some alien. And he goes on, when I see a sentence with two knots, I get rid of the knots, and this is the same in the same page. He says, but this should be taken, remember, he's left the goat out. He says, look, there's a problem here. But now he says, but this should be taken to imply that there are good reasons to believe that it could have started on Earth by a perfectly reasonable sequence of fairly ordinary chemical reactions. Now, that is a major assertion. Now, that is an assertion, so he should then prove it, right? What are these reasonable reactions, right? Give me some good reason. They don't have them. The more they study a cell, the more they realize it's impossible. And this is an important thing to realize when you're talking with someone about evolution, and particularly chemical evolution. Natural selection has nothing to do with it. Because when you have natural selection, you have to have genomes, right? A male, female, right? Male, female, and they produce offspring. That's where the natural selection occurs. Here, if you read it, natural selection is a differential reduction, organism perpetuation. In order to have natural selection, you have to have self-reproduction and self-replication and at least two self-replicating units of entities. I would like to plead with you simply, please realize you cannot use these words natural selection loosely. Pre-biological natural selection is a contradiction in terms. These are the own people on the other side saying, don't even talk about natural selection when you're talking chemical evolution, origin of life. Because you have to have information, DNA, in order to have it carried out. Now, how many of you have heard of the Harvard's Origins of Life Initiative? I'm sure you haven't. Maybe you have. Well, they said they had lots of money from the taxpayers. And they said, we got to figure out this origin of life thing. This is becoming a problem. And what did they do? They formed this initiative at Harvard, all right? And they hired a really smart guy. They got a group of chemists, and they're looking at it. If you read it there, it said, is it easy or hard for life to emerge from the chemistry of early planets? In the lab, we try to work out a complete step-by-step plausible pathway of all the way from simple chemistry to more complex chemistry to simple biology. Remember though, the LUCA, right? He goes on. We are looking at a very narrow slice of the whole problem, he says. We assume we have the chemical building blocks of life. He's assuming he has the chemical building blocks of life. You have to explain where they came from. They don't ever explain it. In most assertions, they never tell you where the genomes come from or the DNA comes from or the recipe of life. Now, finally, homochirality. We're there. I just wanted to show you that, hey, we're without words. We don't know how it started. If I've talked with some of the origins of life guides, and off the record, we have no clue. That's what they'll tell you. We have no clue. But we still believe, given enough time, we'll figure it out. They haven't. They've been going at it for almost 15 years, and they said, well, They moved up to taking the DNAs and all these other things and trying putting them together. And we talked last week. Jonathan Wells said they've done that already, and they can't put it back together. They can't put Humpty Dumpty back together. If they take a cells apart, take all the pieces, they can't put it back together.
It seems to me like maybe you could talk about, the God of the gaps, and how what you're talking about there, that's kind of the science of the gaps.
Oh, exactly. Exactly. Well, natural selection is a God of the gaps for them. In fact, Richard Lowenstein, who's quoted many times, he's the guy that says, in spite of all this, we cannot let the divine foot in the door. Some of you have probably heard that. But he has also said that using the word natural selection just to buzz somebody off is not science. He says when you do it that way, they're using it in a term in a non-falsifiable sense. If something is non-falsifiable, it's not science. If you have a theory, you then try and come up with it. Well, let's see, how good is this theory? Well, if I do this and that happens, that disproves that. Well, they do that all the time. It shows the more they do that, they did that with general relativity. It kept getting stronger and stronger. They kept trying to defeat it and they couldn't. Now, okay, I diverted there. I do go down trails. Now, you're supposed to, Michaela, could you hand out the pasta, please? All right. While she's handing out, we're going to learn about homochirality. All right. Everybody knows the left hand and the right hand, right? You all brought them with them, right? Hopefully nobody's having a sling, right? Well, did you know that this hand is a mirror image of this hand and vice versa? Did you know that? They're mirror images. Now, there's a key thing. They're also non-superimposable. You can never put something that is chiral, overlap it. They're not superimposable. It's that simple. You have an object, a molecule maybe, or any object. If the mirror image is non-superimposable, it is chiral. They're both chiral. Now, if I only have one of those, if I'm only left-handed, all right, that's homochiral. Everybody raised your left hand. That is a homochiral raising of the hand, okay? Thank you very much, Jimmy. Put them down. I appreciate it. Same thing for the ear. Understandable, right? You're all on tune with this, right? Now, if you look at, that's supposed to be like the interior of a car, and it shows the mirror image. That's non-superimposable. Now, there's another thing you can think about when you're trying to determine if something is non-superimposable. Can you divide that object in half and have the same thing where one is superimposable on the other? And I've showed, now these are called chiral objects, all right? And if we only have one of them, that's homochirality, all right? It can be either one, but we only have one of them, all right? Only one of them. That's homochirality. Now, if I put the letter A in the front of chiral, just like if I have symmetric and I put an A in front of the word symmetric, that's asymmetric. Symmetric has a point where you can divide it in half. Asymmetric means it's chiral. So going backwards. I shouldn't probably brought that up, but using the letter A, what do we do when we're theists? People don't believe there's a God. They are atheists, right? So something that the mirror image is superimposable, or you can divide it in half. It has a point where you can divide it in half. Now, does everybody have their penne? Hold up your penne. If you were listening, where's your penne? Oh, you didn't get a penne? It's really simple, right? Is that chiral or is that achiral? Dun, 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 dun. Thank you, Michaela.
I'm just holding up my pen.
That was a homochiral raising of the... What would you say? How many say it's chiral? How many say it's achiral? That's right. It has a plane of symmetry in it, right? You could cut it in half. Now, there are some little fine lines on there, right? if those aren't symmetrical about that object, it wouldn't be chiral. It would be chiral then, but it is achiral. Now, hold up your rotini. All right, that is a right-handed rotini. And it's a triple helix, by the way. So next time you read it, hey, hand me the triple helix over here, please. Now, is that chiral or is that achiral? It's chiral, yes. Because the mirror image of it is non-superimposable. Now for you people that are mechanically inclined, I'm declined, and mechanically inclined, how many have, the first time you hooked up a propane tank to your grill, you're going, you're going, what's wrong? This doesn't go on. I'm strong enough to put, it's a left-handed thread. So right there in the real world we have it. But you have it in the real world, that just happens to be right-handed because of the way you turn it, all right? All right, so I think we're caught on. Anybody have any questions? If its mirror image is non-superimposable, it's chiral. Are you with me? That's the same thing like this. This is for my low budget talk when I'm trying to get funding. Let me see. There we go. See how one's a mirror image of the other? They are chiral. Now, they also have a fancy name for this property. A fancy name called race mates. This is not racism, race mates. And I chose this one because that car is probably from a car that races. You'll never forget, right? You'll forget. But those are called race mates. Their relationship, they're called race mates. Now, guess what? Thinking back to the Miller-Urey experiment, that's all it ever produced. It produced a mixture of race mates, the same amount of left-handed and right-handed amino acids. And we're going to look at the left-handed amino acids shortly, okay? So that was the problem. It never was even talked about and still isn't, even in the biology books, because nobody wants to spend time, laborious time, about doing this. But it's very important because it's so key to building the structures that are in the cell. So let's see, where are we here? All those are superimposable. Now, this is a higher buck Tinker Toy thing. Again, the same thing as I just showed you with the low buck, right? Those are chiral, right? One is a mirror image of the other, correct? And as I mentioned, and want to say it again, their mirror images are non-superimposable. And this would be a homochral picture because we're only showing one of them, all right? And that's exactly what we have in the biological world. Everything is homochral, especially only if around a carbon it has 4 different things. 4 different things. See? 4 different things. Now, normally in chemistry, in the models, black represents carbon. That's probably a good choice if you think about coal and oil and all that stuff. And then you put the other things around it. Now, all right. Let's get to the amino acids finally, all right? So we did the left-handed and the right-handed. And over here is called the L. They call those the L amino acids. I think I have it up. Oh, sorry about that. What did I do? There we go. All right. Now, in amino acids, it has an amino group, amino acids, all right? And it has an acid group, amino acids. That's why they call them amino acids. Now, the distinctive thing about them, and you see it's 4 different things, a hydrogen off one carbon, and they're pointing to the corners of a tetrahedron, an acid in another corner, an R group. And that's what differentiates amino acids from one another, by the different R groups. But in the body, as I mentioned, nope. I'll figure this out yet, guys. Here's an example of amino acid where the R group is a methyl. you see that methane, you get rid of one of those hydrogens. This is the methane right here. You get rid of a hydrogen so you can stick it on the amino acid. That's a methyl. Pretty simple, straightforward. This chemistry is easy, actually. All right. But if we have only the left-handed, we call that homochiral, right? Now, we're not going to spend a lot of time. There's not going to be a quiz on knowing all these amino acids, but these are amino acids that your body needs. And there's 20 of them. Now, what I want to point out is a couple things. There are some amino acids that are hydrophobic. Does anybody have a problem with hydrophobic? No. Hydrophobic means it doesn't like water. It can't dissolve in water. All right? It would rather dissolve in something like gasoline. All right? Something that's hydrocarbon. Hydrocarbon, all right? That's more oily-like part of the molecule. Now, it turns out there are hydrophilic. Those are water-loving, right? Hydrophilic. So these dissolve in water because they love water. Now, if you can remember, also, if you want to, remember this aspartate, that amino acid, you can see the negative charges around that? You see, everybody see the negative charges? That's because we had an acid group, COOH, and we took off a proton. What charge does a proton have? It has a +1 charge, right? So if you take a +1 charge from a molecule that's neutral, what's the remaining molecule? Negative, right? Because you now have a plus proton, you have a negative acid group. That's why those are shown as being negative. And that's what makes them hydrophilic. Now that's important, and we're going to take a quick chemistry class, and you all know how to do this. I'm leaving the cat out of the bag as to where's our chemist? She's not here tonight. Oh, there she is. Oh, sorry. Are you sleeping yet? Oh, sorry. Well, chemistry is simple. It's just molecules and knowing anything about electrostatics. You already know it. What do we know about electrostatics? A plus charge and a negative charge, what do they do? Repel or attract? Attract. Unlike attract. Like repel. If you know that, you can be a chemist. And if you are how many people studying accounting? Well, to be a good chemist, you just got to be able to count your electrons and your charges, your pluses and your minuses, and you can figure it all out. It's simple. We already said that. We all know that. On the atomic level, we know already, it sounds like, that everybody knows that electrons have a negative charge. Electrons orbit the nuclei. Nuclei atoms are positive. The nuclei of an atom is positive. And if you have a neutral molecule, it's an equal number of plus and minus charges. Now, I mentioned about water being unique. And stick with me if you don't mind. Here we have a water molecule, and I actually have two here. Water molecule also has a tetrahedron build. If you look at it, you see these little gray things? Can you see them? Those are spare pair of electrons. That's what I'm showing there. Now we all know that electrons have a negative charge, right? So we have these two molecules of water. Because this is a partial negative charge out here and a partial negative charge there, and the oxygen is pulling electron density towards itself, letting that little poor proton being somewhat bare, and this positive charge is now showing. Remember, a proton has a positive charge, right? So what happens is you have negative this side of the molecule, and you have positive this side. So what happens is, because of that separated charge, water has a dipole. And because of the partial charge, we call it a polar net dipole. This is a space-filled representation of water. All right? Now, if I had a solution of water, because of thermal energy, they're moving around. if you heat up water, they move further apart. And eventually what happens, they get enough energy to escape the liquid and become a gas, like in Miller experiment, right? So they're moving around, and the dipoles are interacting, but because of the thermal energy, the dipole interaction between the plus end and the negative end of two molecules, they'll be attracted this way because their dipoles are lined up, right? This is a positive end, this is a negative end, so this is negative, it's going to be attracted this way. Now, what happens as you cool this molecule? What happens is you start getting something, a phenomenon which you have to know, and that's why we're laboriously going through this. Sooner or later, what happens is it slows down, you end up with this proton, which is positive, and this electrons, which are negative, that's what the density measure is, all right? They line up. This is called what? Hydrogen bonding. This is so critical, and I'm going to show why, all right? Not only we need this homochirality, we need hydrogen bonding. Thank you, Lord, for hydrogen bonding. Remember Thanksgiving? Lord, thank you for hydrogen bonding. That's actually holding the turkey together, actually. That's what's holding your DNA together. That's what's holding all your proteins together. Hydrogen bonding. That simple attraction. So what happens, slowly, once you get to 0 degrees centigrade, they stop moving. And then they line up like this. You can now see through. There are holes. Now, oxygen will not pass through there. Now, does this ring a bell to you? When I was a little kid, okay, everybody knows there's a unique property. Only water seems to do this. When it freezes, it what? Expands. That's why it expands. It lines up. There's actually holes. It occupies more space. And that's why it expands. Now, this is important. Now, oxygen doesn't go through there. When you have a frozen pond, the oxygen actually goes through the crystal lattice. This would be a crystal. It would go along the edges, all right? It doesn't fit in there, but that's why it expands. That shows you how powerful this hydrogen bonding is. Only from a simple water molecule, but we need that, understand that. Everybody understands. Now you can have other atoms. You can have other atoms involved in hydrogen bonding. You can have a nitrogen hooked to, are you with me there? Did I leave you? You can have a nitrogen with a proton. This, I'm sure I should explain. The white is a hydrogen. The blue is nitrogen, okay? So what can happen is you can actually get hydrogen bonding with this between the negative electrons and the proton, all right? Very key. That's why it goes to solution. In fact, remember I was saying with that acid that had a negative charge? It was negative. What end of the water molecule is attracted to the negative charge on a carboxylic acid? The positive end, right? This end. So that's how everything, if something is positive, the negative end, solvate, goes around that charge. If something is negative on a molecule, water then has its positive end at that charge. Okay, now, everybody knows if you take amino acids, and we already got this far. The problem is, the homochirality problem is, the fact that in nature we only find the L configuration of the amino acids. Now this is again another cartoon, but we're going to get a little bit fancier. The point is to show you the different structures of proteins. So we connect. We don't have time to show, but take my word for it. What happens is the amino group of one amino acid reacts with an acid group of another amino acid, and you build a chain, you build a polymer. Some call it a peptide, some call it a protein. All right, so we have them, those the amino acids. You see the lysine, glycine, leucine, valine, and all that good stuff, all right? You have a chain, a biopolymer. This is what you expect to form if you have the amino acids. It does not happen in water. We can talk about that later, why it doesn't. Now, what happens is, just like your rotini, it's an alpha helix. It spirals. I bet you never heard of proteins doing an alpha helix. You've heard of DNA doing the alpha helix. But a protein also does it. And I hate that drawing. It's so bad. So I found one a little bit better. Now, what is holding that alpha helix together is, say the magic word, and it's hydrogen bonding tonight. All right? What's happening is the hydrogen on the amide bond of the protein, nitrogen, okay, hydrogen, oxygen, the spare pair of electrons on the oxygen. That's what holds that alpha helix together. Just simple attraction electrostatics. That's what holds it together. That would be looking down the center of the alpha helix. This shows you how the R groups fall off. You see how they kind of lean this way as the alpha helix is going this way? You see that? See how they're falling down? That's why if you had one D in there, it would mess this alpha helix up tremendously. They all have to be L. So you get the alpha helix, and you can build these fantastic proteins. So what actually happens, you get the alpha helix working, and then there are reasons for folding happening, and you form this type of thing, which is, they call it a tertiary structure. And then what's really amazing, in this case, I'm having an example where you have 4 of these, they're all the same, fit together. Guess what holds those together? There's no chemical bonds. It's hydrogen bonding. That's why we went through all that problem. And it's also hydrophobic effects. Those R groups that are hanging off the alpha helix that are hydrophobic, they are attracted to each other and holds it together. So this is all held together, and it fits like a glove. It all happens because all those amino acids are L. I have here, that's a calculation to show what the probability be to form an amino acid with just 100, 10 in one part to 190 would be the probability. 10 to 190. That's just only for a protein that's only 100 amino acids. All right? Most in our body are between 3 and 400, 2 and 400, yada, yada. But if you take one of those and you put 4 together, here's an example of all different types of biocatalysts, enzymes that do all kinds of unique reactions. Every reaction on that metabolic pathway involves one of these guys. And they don't work unless you have the L amino acid. You have hydrogen bonding working intimately with all the different groups on the molecules. Now, one example. Remember I said that one bottle amino acid, the D-aspartate. Now, well, the L-aspartate. This is what happens if on the protein you go from the L-aspartate, which was on the original protein, and it enolizes and epimerizes to the D. And we don't have time to show that. Oh, it is on the notes, though. I'll be glad to explain that to you if you're interested. But just saying it, the L has gone to the D. And look, I'm sure you're reading, look at the different problems that happen just by one amino acid changing from the L to the D. Now, how do you know that your body turns over proteins in your over a certain amount of time? Every 7 years, all your proteins have been turned over. That helps keep away from this. You're not the same you as you were 7 years ago. So we can tell somebody that. I'm not the same me anymore. Well, it took a while, but I'm not the same me. But that's a simple example. Now, this is an example of just changing one amino acid to another. You with me? Changing one amino acid in the protein to another. This is actually hemoglobin. All right, and it's, as you can see, it's four different proteins forming a tetramer. And this red thing, that's the heme part. That's the part that holds on to the oxygen in hemoglobin. Now, if you change just one of those amino acids to a different amino acid, obviously it's a critical spot, all right? What happens? You know what happens? Sickle cell anemia. Just one of them changing. I'm not going to read all that stuff there. I think you got the point. But that total amino acids is 574. That's how many we change one. So guess what our friend Richard Dawkins says? That's not a big problem. Because what they do is they kind of do a reductionism. They say, well, we don't need these, we don't need those, we don't need these. Oh, we need those, we don't need those. But they haven't done the experiments. Just like they always say, well, just some reasonable experiments. They don't do the experiments. So what does he say? He says, well, it looks like, I'll read it for you. It looks like we only need really 190 of those amino acids. Those particular ones have to be there in that molecule, in hemoglobin. And I think I did, yeah. The chance of just forming that is 10 to the 246. You with me on the 10 to the 246? That's 1 with 246 zeros behind it. 1 out of that many. Now, here's another thing about sickle cell anemia. What is the cool thing about people who have sickle cell anemia in Africa, or the places where malaria is the problem? They don't get malaria. They make it. So what do evolutionists say? Aha, that's a form of beneficial mutation. Now, it was a loss of information, but the species survived. So they say, well, see, that's an example. But what is the net amount of information gained or lost? It turns out, do you know that when two male and female produce offspring and they both have the same defect, that offspring perishes, doesn't last. So what shows they're not looking at the big picture. When you've lost information, you pay. So they say that's evolution, but they never explain where the hemoglobin came from in the first place.
So short-term gain, long-term loss.
Yes. I'm gonna get into it. I'm trying to keep it to, I'm almost there. Thanks for hanging in so far. You could say more about this, but in the Michael Behe's book, Edge of Evolution, he talks extensively about that. He talks about how it's impossible to have two supposedly beneficial mutations and working and really help the species. They have a benefit from it. All right. So, quick example of there are so many different types of proteins, it just blows my mind. Now here is a tetrahelix, all right? You see there's 4 of them in there supposedly, and it's showing the R groups coming off remember the R groups in amino acids? Those are extending off these alpha helixes, and that's what holds them together. And what happens is, this shows how gets rid of them so you don't see them. This forms this, and it forms a bundle, fibrils, and that is what your hair is made of. Did you ever look at a cross-section of the first intercontinental cable for phones? It looks just like that. One bundle after another, wrapping around. In fact, Actually, they do wrapping. Amazing. Okay. We are copying a lot. I'm going to finish with something really cool to lead into next week. We're going to do DNA, or whenever we do this, right?
I thought we were doing the documentary next week.
You're doing it. That's right.
Whatever you want.
No, I want to do whatever you want to do. We'll do a documentary. They need to cool. We need a cooling off period.
One thing is, next week there won't be many people here.
Yeah.
I want people to hear what you're saying.
Oh wait, yeah, we need more people. But what I'll do, I'll kind of review just what chirality is, all right, and then we'll get into DNA. Where is the chiral substance in DNA that causes the alpha helix to work? Now, having said all that, there are 8 proteins in there. That's what those squiggly things are, the alpha helixes. There are 8 of them, and they form like a spool for, I think it's like about a 1.5 turn of DNA. See the DNA in here? And by the way, what's holding that DNA together? Remember, key thing? It's just hydrogen bonding right in the middle. That's all. Hydrogen bonding. And there's hydrogen bonding going on in there. Plus the hydrophobic effects too. Things which are hydrophobic, they are attracted to each other. So that's an example. It's actually wrapped around a spool. And next week I'll show you how DNA is, well, not next week, I'm sorry. How DNA is stored in a nucleus. It's incredible. This close to final slide. Now, what's really cool, and another reason for bothering you to talk about something as simple as water, which is an incredible molecule, to say the least. Some of those where you have hydrogen bonding, oh, they say this hydrogen hooked to an oxygen, he can't reach to those electrons over there. So what happens? Water acts as a bridge. Acts as a bridge between those two, so hydrogen bonding is intermediated by the water molecule. And what this shows is every one of those water molecules has a function to hold that together. Is that amazing? To me, that's amazing. And I have some others, I'll show them maybe next time. It shows this branching, you know. How's that guy? Well, water sits right in there. Some of those enzymes, they actually require 1 molecule of water sometimes for them to work. Without that water, that particular size, and this is like an anthropic principle. Man would not be here without the fine-tuning attraction of the hydrogen bonding and also the right configuration of the atoms so we have chirality. And you need the chirality to get the spiral, the alpha helix. And we'll skip that. There's not much in the scripture. Now, I can always remember this because 139, oh yes, 13. Everybody's familiar with that, right? Who would like to read it?
Sure. For you formed my inward parts. You knitted me together in my mother's womb. I praise you, for I am fearfully and wonderfully made. Wonderful are your works. My soul knows it very well.
Woven together? Are you kidding me? It's like a thread. Have you ever taken a thread and just unthreaded it? It's a helix, a mixture of helixes, right? And that, what holds that together actually is there's some hydrogen bonding going on there between the threads. Knitted. For those still awake, you may have a question. I appreciate your time and staying awake. Everybody hung in there. You guys are tremendous for being up this late and eating pizza and cookie. By the way, take some home with you. They're really good for you. Got oatmeal. Oh, it's black walnuts and chocolate inside. It's the best. That's it. I've had enough. Whoever's watching this, God bless you.
Maybe if you could say if anybody watching has any questions.
Oh, if anybody watching has a question.
Yep. Feel free to type it in.
What else you want me to say?
That'll work. Does anybody have any questions?
So you were saying the homochirality, it's been a long time since I've been in chemistry class.
You know what?
A long time.
There are very few clergy that have even taken one science class. And that's the problem.
So you're saying the homochirality is the problem for...
Homochirality allows you to produce proteins that give you an alpha helix so you can build those fantastic structures. They all got to be L. And if one goes goes to D, you saw it was catastrophic. Now, granted, it was select one, but it's very critical. I didn't have time to show, I should have showed you where those R groups are, but if you have a D in there, it just doesn't work.
So you're saying that the homochirality can't happen through natural selection?
No, it's not. Here's a simple rule. It takes chirality to make chirality. There was no chirality here. There is some thought that certain astronomical objects emit a certain type of radiation that has chiral. That's chiral. The point is, in all their attempts, I have visited hundreds of pharmaceutical companies around the world. Each year, they spend billions of dollars trying to make a single isomer. They can't. The best chemists can't even do it. Now, there's some reactions that are pretty good, but most of them, that's what their effort is. Do you remember telluromide? Telluromide? No, wait.
I don't know what you're talking about.
Thalidomide. Remember thalidomide back in the 70s, I think it was? It was a mixture of an L and D molecule. One of them was good for sedative hypnotic, but the other one was teratogenic. And they didn't know that. And then what happened? Birth defects. So ever since then, hey, we got to have just one. And what made this one worse, this one could go from the L to the D. Trouble City. I don't know if you've ever seen the pictures of the kids that were born. No arms, no legs. It was horrendous. Scientists are always trying to figure out a way to do it. And what really is kind of funny, it's not funny, it's sad. Anytime a physicist discovers a new law, he figures out how something works. I got this law, I got to figure out, don't need God. We see a guy go and do this experiment. Oh, I see how amino acids are made. I don't need God. Their problem is they don't know how, they don't recognize mechanism and law with agent. They don't understand the difference. You need an agent. With the cookies, I have my grandma, she made Pennsylvania Dutch, by the way. She made the best cookies. There are some in here I tried to, she only had the ingredients, not the amount, not the order. And you know, baking is the most precise form of food preparation.
It's a science, literally.
Yeah, you have to have the recipe. You have to have the ingredients at the right amount. And thinking about it, it still doesn't make a cookie. What do you need? You need an agent. You need a cooker. Right? Behe's mousetrap? Yeah, that's true. It's an irreducible object. The mousetrap, you take out a part, it doesn't work. But that's not the whole story. You need someone to make the cheese. You need someone to load the trap. They're leaving out the agent. And they don't leave it out. They confuse agent with law and mechanism. And John Lennox is really good at doing that kind of explanation. Does that make sense? We can talk about that more.
They're just ignoring the fact that you need an agent.
Exactly. Because if they admit an agent, there may be a God. But you guys did something on cosmology, I'm sure. The most advanced scientists who know something about cosmology, they say it was an outside agent. You know, what did Stephen Hawking's, who was it said? Yeah, if general relativity is true and gravity works, there has to be an outside agent, an uncaused cause. There has to be. And when scientists create in the lab, create life in the lab, they're going to say, we don't need God. But where did they get the dirt to begin with, right?
Well, and in that case, they're an agent.
Yeah,
They
exactly.
have proved nothing.
Yes, exactly.
Except that you need an agent to make it happen.
Well, you ever see that picture of a scientist? He has in the back there's checked off the number of experiments he's done, and he's hunched over. He says, if I get this to work, I'll prove it takes no intelligence for life to happen. You know, he's done thousands of experiments, right? I would like to draw in the corner a Bible with cobwebs on it. Because if they would have used that, they would have realized a long time ago there was a beginning in the universe. A long time ago. In fact, the Bible is filled with prophecies of things to be discovered. Job has 64 questions. You know, they gave a little quiz. Well, we're up to about, I think, maybe half of them. We've answered half of them. God doesn't ask non-trivial questions. I'm going down an avenue here. He doesn't. There are questions to be answered. And you know what's happening? I'll get off the soapbox. We don't understand what gravity is, but Newton, he had a good key hand on it. We don't understand what dark energy is. We don't understand this. You know what it is? We're getting up to the point in every field where we're bucking up right against God. And we just say we don't know what it is. That's it. It's a cop-out. But then you say, well then, as I said last week, well, have you ever considered, if we don't know, shouldn't we bring an outside cause in? If you're really interested in that kind of approach, I recommend reading James Warner Wallace, Golf's Crime Scene. It's awesome the way he does that. Anyway, I'll shut up. Another question?
So, just want to make sure I'm understanding this right. So, the chirality is important so that the proteins it makes don't mutate into something terrible. And if it came about naturally, there wouldn't be anything to prevent these right or de-orientation things. So it had to come from a ribosome which was already tuned to make left-oriented things.
Oh, there are check systems to make sure that they're made right.
So that's the problem with it then?
Pardon?
So that's the problem with the natural.
Yeah, well, yeah. In fact, they do point to the generation of RNA, messenger RNA. We're ahead of ourselves. We'll learn about messenger RNA. Maybe you already know about it. But the ribosome, the system rejects 20% of those that go there. They say, look, it's not perfect. It should be 95. Guess what? People were searching and they found that the reason that doesn't read all of them, everyone that comes to the ribosome, is because it's hooked to the immune system. Because of that extra 20%, the body is able to react to invading RNAs. This body is so complex. We don't give enough credit to how fantastic it is. We think right away we got to have a drug, we got to have a vaccination, we got to do this. It's made to withstand. All right. Now there's a law of entropy. We can't battle that one. We always will battle that one.
Any other questions?
I appreciate your time. You can take your twist steady off.